Welcome to lecture 4 on earth pressure theories. In the previous lecture, we have looked into the Rankine's theory and assumptions relevant to Rankine's earth pressure theory, and we also discussed about special cases for computing earth pressures and extension of Rankine's theory for a special case like inclined face of a wall and with inclined slope face. In this lecture, we are going to introduce another theory called Coulombs earth pressure theory, and subsequently we look into the graphical method for solving or computing earth pressure. This is by using trail wedge method, or is also popularly known as Coulombs method. So, in the previous lecture, we have discussed and we have said that two states which are going to be prevalent. One is that active and passive. Active can occur when the wall moves away from the backfill. Passive can occur when the wall moves towards the fill. So, here a cross section of a sheet pile wall is shown, in which this is the embedded depth level, and about this level it can have some active zone if this wall is rotating about this point, and this can have a passive zone. So, here in this case, this portion of the soil will be subjected to compression and this portion of the soil is subjected to extension. So, the remaining portion of the soil will remain in elastic equilibrium conditions because of the prevailing roughness conditions. So, this we said that 45 plus 5 by 2, and this is the failure surface, and this is the possible failure surface in case of passive case. And we discuss a failing backfill behind outward yielding wall. So, in this slide, a typical cross section where wall yielding away from the backfill soil is shown. In this, we can see along this surface, when a surface which passes through this, a plane which passes through this heel of the wall satisfies the Rankine conditions. So, here along this it mobilizes the failure shear stresses, and then along this it develops a shear plane. So, here a returning wall when yields away from the backfill, and this is the stress state at a particular element along the failure plane. So, we also discussed about a Mohr strength diagrams. Here the development of the Mohr strength diagram during the progressive outward wall direction is shown here. So, this is the vertical stress is shear stress and horizontal axis is sigma. So, initially this is the at rest stress circle, that is this is the at rest conditions. So, this is sigma h naught by sigma v, k naught is the coefficient of earth pressure at rest. So, once wall starts yielding, the pressure starts decreasing and it attains a value sigma h a minimum, and then attains the failure along that shear plane which was shown in the previous slide. So, this is how that progressive outward wall movement induces failure to a element under consideration. Similarly, when you look into the another case called passive case, in this case a failing backfill behind inward yielding wall is shown. So, this wall, returning wall, is yielding towards the backfill. So, induces a compression in this case where along this shear plane it actually induces tau alpha, that is the shear stress which get mobilized and the wedge of the failure. So, sigma v and with the vertical stress and sigma h is the horizontal stress. So, in this case the sigma h becomes the major principal stress, sigma v becomes the minor principal stress. So, let us see how the development of the Mohr strength diagram can be there during the progressive inward wall deflection when the wall moves towards the backfill. So, here again at rest circles are shown here. So, this sigma h naught changes and surpasses sigma v. For a given sigma v, it develops sigma hp, finally attains, this is the passive at pressure and attains failure. So, this is how the development of the this progressive inward wall deflection can be shown in a Mohr strength diagram with systematic Mohr circles which are shown here in this slide. Now, before discussing Coulombs theory, in the last class we discussed about a vertical smooth wall with inclined slope surface. Ideal Rankine wall is with a vertical wall which is smooth in nature and horizontal surface, which is the backfill surface, is horizontal. But a case where which can be extended, this Rankine's theory can be extended by assuming that the stresses which are sigma A parallel to the slope surface. So, from the discussions which we have made in the previous lecture, we can solve this problem. A vertical smooth wall of 6 meter high and retains a soil with a slope of 20 degrees. That is, the slope of this surface is 20 degrees with the horizontal, which is shown here. Determine the total active thrust on the wall. The shear strength parameters given as cohesion is equal to 0 and friction angle which is drained 40 degrees, and unit weight of the soil is 18 kN per meter cube. The height of the wall is 6 meters. So, using in the previous class we discussed about Ka is equal to cos beta minus root over cos square beta minus cos square phi divided by cos beta plus root over cos square beta minus cos square pi. By using this we can get Ka is equal to 0.265. By using Pa is equal to half Ka gamma h square cos beta, we will be able to get the active thrust on the wall. This is how you can solve analytically. The same solution can also be done by plotting Mohr strength diagram, which we will see in the next slide. But here the earth pressure diagram which is shown here, this ordinate is nothing but Ka gamma h cos beta at depth z is equal to h, and this is the Pa which is acting at h by 3 vertically from the base, and Pa is equal to, which is shown here, of Ka gamma h square cos beta. So, for the given condition in this problem, the lateral thrust which is acting parallel to the direction of the slope surface, that is 20 degrees with horizontal, is 81 kN per meter, and at a height of 2 meters from the base, that is h by 3, h is equal to 6 meters, so 2 meters from the base. How this can be solved graphically? Let us look into next slide. So, in the continuation of the previous example, beta is equal to 20 degrees, that is the surface, and friction angle is 40 degrees. So, let us plot this on a tau sigma plot. So, on the tau sigma plot, first failure envelope is known to us. The failure envelope is inclined at 40 degrees with the horizontal. So, plot this on the Mohr circle. Then the ground surface is 20 degrees with horizontal. So, plot ground surface. So, on this ground surface along this direction the stresses are acting, please remember. So, now at a depth of 6 meters, that is at z is equal to h is equal to 6 meters, sigma z is equal to gamma into h cos beta, which will give us 102 kilopascals or 102 kilonewton per meter square. So, with that, set 102 kilopascal to a scale and draw and represent along this particular 20 degrees line, that is this surface line. So, OA is equal to 102 kilopascals. So, represent with say 1 centimeter is equal to 10 kilopascals or with some units, and represent on the Mohr circle. So, from here if you draw a line, the point where it cuts, that is the pole which is drawn generally from the known stress on the Mohr circle. So, this is a point B. So, with the point where, from the point where pole is there, from there if you draw a line to envelope, failure envelope, if it cuts at F, so by seeing that it passes through F and it passes through A and pass through B, if you draw a Mohr circle, you can construct Mohr circle by satisfying these conditions. So, once we draw the Mohr circle, so sigma A is equal to 27 kilopascals, or that is nothing but either OB or OB dash, both are same. So, with this we will be able to get that is active earth pressure ordinate, that is 27 kilopascals, which is either OB or OB dash. So, then PA, that is active earth pressure thrust, is equal to half, that is sigma A, which is the base, and H, which is yields to about 81 kilonewton per meter. So, inclination of the failure planes BF and BG can be measured. So, BF is 59 degrees with horizontal, and BG, which is the another failure plane, which is 71 degrees with the horizontal. So, by using these concepts, now we can even also by more strength concepts, we can also solve this problem graphically and compute active thrust. In this problem, what we did is that we keeping the soil properties under consideration and the geometry of the slope surface, we calculated the earth pressure coefficients. From there, we tried to solve by computing the earth pressure ordinate at a depth z is equal to h is equal to 6 meters, and then active thrust has been calculated. The same problem we tried to solve by using Mohr strength diagram. Now, having discussed Rankine's theory, but we knew that many situations, most of the retaining walls which exist, they are not rough they are not smooth in nature. In such situations, the Coulomb theory of earth pressure, which was put forwarded almost 1 century prior to Rankine's theory, but we discuss Rankine theory first and then Coulombs theory later, because of the only difference, the chief difference between Coulombs theory and Rankine's theory is that in Coulombs theory, Coulomb considers the friction between the wall interface and soil. That is very important, where it has got lot of effect on the earth pressures which will act on the wall. So, as we discussed just now, the back of every real retaining walls is rough to some extent. So, the back of every real retaining walls is rough to some extent. So, the boundary conditions for the validity of Rankine's theory are seldom satisfied. So, the ideal Rankine's conditions are seldom satisfied, like smooth vertical wall or with a fill surface horizontal. In such situations, we have to resort to Coulombs theory. So, earth pressure computations usually involve an appreciable error if we are able to deal with Rankine's theory with the assumption of negligence of the friction between the interface wall soil interface. So, this can be avoided by adopting Coulombs theory. So, Coulombs earth pressure theory involves a simplifying assumption regarding the shape of the sliding surface. It has got a assumption which is called a sliding surface is assumed in this theory. But though with this, despite of this limitation, another limitation is that on the failure wedge, the forces were not under equilibrium. But despite of these demerits, the theory has got a merit over Rankine's theory. So, the Coulombs theory of earth pressure always superior, because the real retaining walls always have a friction between wall along the wall interface and the soil. So, this can be avoided, and the error which can cause by neglecting that wall friction can be avoided by adopting Coulombs theory. So, Coulombs pressure theory after Coulomb 1776. So, the Coulombs theory is similar to Rankine's theory, except there is friction between the wall and soil, and takes this into account by using a soil wall friction angle equal to delta. Note that delta ranges from 50% of the friction angle to about 66% of the friction angle, that is 2/3 of the friction angle, and delta is equal to 2/3, that is 2/3 times the friction angle is commonly used. Delta is equal to 2/3 times pi is commonly used. That is the friction between the wall and the soil, and takes this into account by using a soil wall internal friction angle of delta. That is the fundamental difference. Then soil behind the wall is considered as a whole instead of an element. Soil behind the wall is considered as a whole instead of an element. And lateral pressure is not limited to vertical walls. So, lateral pressure not limited to vertical walls, you can have a wall with any inclination, and also the backfill surface can be having slope surface, need not necessarily be horizontal, and resultant force is not necessarily parallel to the backfill surface because of the soil wall friction value delta. So, the resultant force is not necessarily parallel to the backfill surface because of the soil wall friction value delta. So, in this slide what we saw is that the chief differences between Coulomb's theory and Rankine's theory we saw, And the fundamental difference what we said is that the friction between the wall and soil, which is actually considered in Coulombs theory, which was absent in Rankine's theory. Now let us look into some assumptions which are involved before discussing about Coulombs theory. The assumptions are: the backfill surface or backfill soil is considered to be dry, homogeneous and isotropic, and it is elastically undeformable but breakable. The granular material possessing internal friction but no cohesion. So it is basically for cohesionless soils which is postulated. The backfill soil is considered to be dry, homogeneous and isotropic, and it is elastically undeformable but breakable, and granular material possessing internal friction but no cohesion. Rupture surface is assumed to be plane for the sake of convenience in the analysis. So this has got to some limitations which we will discuss subsequently. Rupture surface is assumed to be plane for the sake of convenience in the analysis. The sliding wedge acts as a rigid body. It actually, once the failure, it represents as if that the portion of the soil got detached from the rest of the soil mass. The sliding wedge acts as a rigid body. The position and direction of earth thrust are assumed to be known. The position and direction of the earth thrust. Generally, the position which is in a given failure wedge, if the weight of the wedge is at the centroid, and at the centroid location, if a line is passing through the failure surface, and wherever it touches the surface or a vertical face, suppose if the wall is vertical and if it cuts at that particular point, and that is where it is assumed that the active thrust or passive thrust is acting. That means that the position and direction of the earth thrust are assumed to be known in this theory. And soil shear strengths develop along the wall and failure plane. Soil shear resistance develops. It is assumed that the soil resistance or the friction is assumed to be developed uniformly and uniformly along the wall and the failure planes. Another assumption, which is assumptions which are continued in this slide, when the soil wedge is impending, that is either moving away from the backfill or towards the backfill, the theory gives two limiting values of earth pressure, like in Rankine. The conditions are similar. One is active and other one is passive, compatible with equilibrium. So when the soil wedge is impending, the theory gives two limiting values of earth pressure, active and passive, and compatible with the equilibrium. If the wall yields and the rupture of the backfill soil takes place, a soil wedge is assumed to be torn off from the rest of the soil mass. So this is as we discussed in the previous slide. If the wall yields and rupture of the backfill soil take place, a soil wedge is assumed to be torn off from the rest of the soil mass. And friction is assumed to be distributed uniformly, and back face of the wall is a plane. So the back face of the wall is a plane. That is another assumption which we made in this. Then we also discussed in the previous slide while discussing assumptions, the failure surface which is assumed to be a plane. So in effect, due to deviations from the actual plane of failure, here a wall cross section is shown, and here according to Coulomb's plane of failure this is indicated with broken lines here. This is in case of active, and this is the active wedge, and this is a Coulomb's failure surface, and this is a Coulomb's failure wedge. But if you look into it in this figure, in this slide, actual failure plane for active case is this one, which is approximated by the log spiral theory, and if you approximate in case of a passive case, there is a much deviation, and this passive wedge which is actually having a log spiral based on the log spiral theory, and this is the actual plane of failure. Now there is a deviation. The deviation is very clear from this figure. It is minimal in case of active case, but it is maximum. It is the difference is cannot be ignored. May not be acceptable in case of a passive case. So if you look into this, this particular assumption of failure plane, this is the actual failure plane, and this is what it has been assumed as a plane for the sake of convenience in the analysis by Coulomb. So negligible in the case of active pressure due to the marginal deviation of the curvature of the actual plane of failure. So because there is a marginal deviation from the actual plane of failure, so that is negligible as far as the active state is concerned. But whereas in case of passive case, the error remains small as long as the interface friction angle is about 1/3 of the friction angle of the soil. That is, if delta is equal to within pi by 3, then this the difference in the case of passive pressure, the error remains small. But for cases where delta greater than pi by 3, that is the wall interface friction angle delta is more than the 1/3 of the friction angle of the soil, the error becomes unacceptable, and because of the pronounced curvature of the actual plane of failure. So the deviation from the actual plane of failure and the assumed plane of failure by Coulomb increases for the values of delta greater than pi by 3. Now let us look as before deriving Coulomb's active earth pressure coefficients and passive earth pressure coefficients. Let us try to look into different possible types of wall frictions and how they affect and how they can be exist in the field with typical cases. So types of wall friction, let us discuss active case. In active case we have two types of wall frictions, positive wall friction and negative wall friction. Similarly, in case of a passive case, we have positive wall friction and negative wall friction. Let us look positive wall friction. This is for the majority of the active cases in case of Coulombs theory. So this is a cross section of the wall which is shown here, and this is the backfill surface which is inclined, and this is the one of the failure assumed failure surface. So outward stretching lead to downward motion of the soil relative to the wall. So as the wall moves away from the backfill, and also the wall is assumed to be rest on a firm foundation. The wall is assumed to be rest on a firm foundation. In such situation, the outward stretching lead to the downward movement of the soil relative to the wall. So outward stretching of the wall lead to the downward movement of the soil relative to the wall. In such situation, this causes a downward shear force on the wall. So this causes a downward shear force on the wall. So active thrust exerted on the wall is directed with a downward inclination. Because of this downward drag, what happens is that the active thrust is exerted in the downward direction. So that's how the PA, which is the active thrust, is shown here. Now this positive wall friction is indicated, and this is the plane perpendicular to the wall surface. So this is 90 degrees, this angle is 90 degrees. So the delta which makes with this particular surface is the direction of the thrust exerted by the wall onto the soil, that is PA. That is PA which is indicated here, and this case is referred as positive wall friction active case, positive wall friction active case. Mostly for concrete walls, the friction angle is 2/3 times the friction angle of the soil. For concrete walls, the wall interface friction angle is 2/3 times the friction angle of soil. So in this we have seen positive wall friction active case, where the direction which is shown here acts below this surface, below this line which is indicated by positive delta. Let us see the next slide. Assume that the wall is resting on a soft foundation. In the previous case, in the positive wall friction case, in the active case, wall is assumed to be rest on a firm foundation. In this case, wall is assumed to be rest on a soft foundation, or at the crest there is a heavy load has been applied. So negative wall friction which causes settlement of the wall, which may result due to soft foundation or due to load on its crest. So settlement of the wall can arise because of the soft foundation or due to heavy load on the crest. So in case when the active thrust occurs, that is active wall movement is away from the backfill, the active thrust exerted on the wall will be directed in an upward direction, because here wall is moving downwards. To oppose that, there will be an upward drag. So that is the reason why the PA is acting upward direction on the wall surface as shown here. So this is the again surface, this is the line which is perpendicular to the wall face here, which is the wall face which is shown here, and if this is above this particular line, then that is indicated as minus delta. that is called negative wall friction angle. So, the negative wall friction angle case can arise if the wall is resting on a soft foundation or being settled because of the heavy load which is there exists on the crust of the wall. In such situation, the soil, moving soil, when the outward moval, when wall moves outward, it exerts an upward drag. So, because of this, the negative wall friction case arises. Similarly, now the types of the wall friction for the passive case. In previous slides, we have seen active case. One is positive wall friction and negative wall friction. In the passive case, also there is two cases are possible. One is that positive wall friction. This is again same for the valid for the majority of the passive cases. So, in the passive zone, the horizontal compression is accompanied by upward heaving of the backfill soil, and this induces upward drag on the wall. So, when the wall is exerted or moved towards the backfill, and that increases, causes a heaving of the soil. So, this heaving which is shown in this diagram like this, and this is that failure surface, and this is the original ground surface, and this is the heaved surface. So, in the passive zone, the horizontal compression is accompanied by an upward heaving of the backfill soil. So, because of this, the upward heaving of the soil, so oppose that there is a this thrust which is actually acts in the upward direction here. So, the passive thrust which is positive wall friction, which is actually again shown 90 degrees with the wall face, is above this line which is indicated, which is shown here in this diagram. So, this is a case of positive wall friction for passive cases. So, in the passive case, the horizontal compression is accompanied by the heaving. So, because of this, it induces an upward drag on the wall. Similarly, a case where types of wall friction, passive case, but negative wall friction, that is friction angle which is at the wall interface is negative. So, this may arise due to settlement of the backfill soil and appears as if wall is going up. So, if there is this is a existing wall, and this is that failure surface, and this is the original ground surface. So, as when the wall is moving towards the backfill surface, because of the settlement of the backfill soil, it appears, it actually induces the drag on the wall in the downward direction. So, because of this exerts a negative wall friction and qualifies for a passive case. So, this is a case for types of wall friction, passive case, where a negative wall friction can occur because of the settlement of the backfill soil and appears in reality as if the wall is going up. Now, let us consider, we look into the analytical expressions which are derived by Coulomb for satisfying equilibrium conditions. So, let us look into first active at pressure of cohesionless soil. So, let us assume that a wall of height h, this AB is the wall face which is having friction. So, let us assume a case where here positive wall friction, assuming that the wall is resting on a firm foundation, and AC is a potential failure surface or a shear plane where the failure can takes place, or the surface where it gives the maximum active at pressure on the wall. So, beta is the slope inclination with the horizontal, that is the slope surface inclination. Alpha is the inclination of the wall face with the horizontal, and delta is the wall interface friction. Pa is the active thrust acting on the soil block. So, as we discussed, ABC is the triangular wedge, and which is opposed now by a soil resistance R, which acts again with a normal with the failure surface AC, and this line is perpendicular to AC, and then this is the friction angle phi, and this is with the vertical, it is theta minus phi, and this failure surface AC which is the one which gives the maximum active thrust on the wall is, say, assume that inclined at angle theta with the horizontal. So, the same conditions and the weight of the entire wedge per meter length, again in the case of Coulombs theory also, these conditions are solved by assuming that 2D conditions are valid. So, the weight of the wall, weight of the soil within the wedge ABC perimeter of the wall can be computed, and that can be said as W. So, this position of the active thrust, which is assumed like this, if this is the CG and if this is located at this point, a line passing through this failure surface which is inclined at theta, which gives the location of the active thrust, that is at this point. So, the same forces like W and this R and PA which are acting on this triangular wedge ABC for the active case when the wall moves away from the backfill can be represented in the force triangle like this. So, here W which is shown vertical and PA which is parallel to this, that is which is shown here, then R which is the soil resistance along the failure surface, assumed to be completely, the friction is assumed to be completely developed uniformly. So, this R is the soil resistance along the failure surface for the movement. So, this inclination is 180 minus psi minus theta minus phi, and this is psi is equal to alpha minus delta, where alpha is this inclination of the wall face with the horizontal, and this inclination between R and W is, which is shown here, theta minus phi. So, the inclination between PA and W is psi is equal to alpha minus delta. So, this is by solving this equilibrium, and if you look at one of the, as we discussed, despite of the one of the demerits is that the equilibrium conditions are not satisfied. That means that when these forces are acting, all these things are not non-concurrent. They at least two forces will try to meet, and third force will deviate from that point. So, despite of these differences, because of the merit in which the theory has been formulated, has got an edge over other theories, though it has got this demerit of not satisfying the equilibrium conditions completely, but it is widely used. In continuation of previous slide, let us now try to compute the weight of the triangular wedge ABC. So, that can be given by W is equal to gamma into area of ABC into 1 meter, that is the perimeter length of the wedge. So, this can be written as W is equal to gamma into h square by 2 sin square alpha into sin theta plus alpha into sin alpha plus beta divided by sin theta minus beta. So, this is one expression we have. Now, from the force triangle, like we have shown in the previous slide, here the force triangle is shown, PA active thrust, this angle is psi is equal to alpha minus delta, and this is W, that is weight of this wedge, R is the soil resistance along the failure surface, PA is the active thrust exerted by the wall onto the block. So, from this force triangle, now we can write PA is equal to W into sin theta minus phi divided by sin 180 minus psi minus theta plus phi. Now, substituting for W in this, we can get an expression PA is equal to half gamma h square divided by sin square alpha into sin theta minus phi into sin theta plus alpha into sin alpha plus beta divided by sin 180 minus psi minus theta plus phi into sin theta minus beta. So, this we can now try to differentiate with respect to theta. So, theta is an inclination of the failure surface with the horizontal, whichever the surface which gives the maximum active thrust on the wall is computed here as active thrust. So, let us consider the same case, a failure wedge ABC, and let us assume that this is the theta. So, we need to find out the surface which actually gives the maximum active thrust. So, initially we do not know this this particular surface. So, we need to take innumerable surfaces and try to get the so otherwise we can do like for maximum PA, we can differentiate this expression which we derived in the previous slide with respect to theta, and then try to get for angle theta, and from there we can calculate what is PA. So, here the same force triangle is shown, this is W, this is a resistance R. So, in the resistance R has got two components, one is that acts along the surface T, and other one is normal to the surface, that is N, that is N acts here like this, that is through which that angle phi is making, and T acts along this surface. So, R is that resultant resistance offered by the soil along the failure surface, and PA which is along this, which is also has got components like this and horizontal and vertical components. Now, when you have got number of surfaces, the trail surface or a surface which gives the maximum active thrust, and that is taken as a surface or a potential failure surface which can actually give the maximum active thrust. So, among the infinitely large number of rupture surfaces that may be passed through the heel of the wall. So, heel of the wall is somewhere here, and the most dangerous one is that for which the active thrust PA is maximum. So, by using this condition, by differentiating with respect to theta, we can calculate the maximum active thrust. So, by using this PA versus this number of surfaces, you can calculate, and you will be able to calculate what is the P max. So, this envelope is shown here. The one surface which gives that maximum is somewhere lies at certain angle theta with the horizontal. So, for maximum PA, dou PA by dou theta is equal to 0. With that, we will be able to get PA is equal to half gamma h square into sin square alpha plus phi divided by sin square alpha into sin alpha minus delta into 1 plus root over sin phi plus delta into sin phi minus beta divided by sin alpha minus delta into sin alpha plus beta whole bracket square. So, this particular PA is equal to half gamma h square into KAC. So, this KAC is written, this particular portion is actually indicated as a Coulomb's active at pressure coefficient, where here alpha, which is the inclination of the wall face with the horizontal, and beta, which is nothing but inclination of the slope surface or a backfill surface with the horizontal. Then we have wall friction angle, which can be positive wall friction or negative wall friction. So, here active at pressure of the cohesionless soil means we need to calculate PA is equal to half gamma h square KAC. Suppose if you know the delta is equal to say 20 degrees and beta is equal to some 20 degrees and phi is equal to 40 degrees. Based on that, substituting in this, first we need to compute the Coulomb's active at pressure coefficient, and by substituting for a given height of wall, we can calculate what is the active thrust exerted by the wall onto the soil or soil onto the wall. Similarly, after having done for active case, let us try to look for the passive case. So, passive at pressure coefficient, passive at pressure of cohesionless soil. So, basically this theory is developed for cohesionless soils. So, let us assume that consider a wall height h, and this is the positive wall friction angle, and which is 90 degrees to this wall face, and this actually acts a delta, positive delta above this line. Now, beta is the backfill surface inclination, and theta is AC is the inclination of the potential surface, where here in this case, passive case, where the one which gives the minimum value that need to be considered. So, here this is the force triangle, W is the weight of this triangular wedge ABC, then PP is the passive thrust parallel to this, and R is the resistance offered by the soil along the failure surface AC, that is R, and these inclinations are 180 minus alpha plus delta minus theta minus phi, and PP and W, the inclination is alpha plus delta. Between R and W, the angle is theta plus phi. So, now in a continuing to the similar way, we can calculate by adopting the same procedure, we can calculate for the minimum PP. Then we can calculate PP, that passive at pressure rest, passive at pressure thrust, which is can be calculated as PP is equal to half gamma h square into this particular entire expression will come, and this is referred as KPC, that is Coulomb's coefficient of passive at pressure. So, PP is equal to passive at pressure thrust is equal to half KPC gamma h square, where KPC is indicated here. In the similar way, we can calculate active and passive at pressure coefficients for the Coulomb's case. Cases can be sometimes delta is equal to 0, and sometimes you have got beta is equal to 0. Then you can reduce Rankine's cases again, and these when you put delta is equal to 0, that is wall friction angle, and beta is equal to 0, and alpha is equal to 0, then it changes into KAC is equal to KA is equal to 1 minus sin phi by 1 plus sin phi, and KPC is equal to KP is equal to 1 plus sin phi by 1 minus sin phi. It changes into this Rankine solution. So, this Coulomb solutions can be converted into Rankine solution by adopting the proper suitable boundary conditions. So, active and passive pressure rough wall, that is with this particular interface, for alpha is equal to beta is equal to 0, these are the conditions, active case, and for passive case. The similar case, the difference is that, as I said, for alpha is equal to beta is equal to delta is equal to 0, the solution converts to Rankine condition and fulfills that ideal Rankine's case. So, in this case, this particular portion is completely plastified, where the plastic equilibrium prevails, the rest of the portion is under elastic equilibrium conditions. So, PA, that is here it's horizontal, which we can be found out again by when substituting this, they change into this corresponding Rankine's coefficients. For a special case where alpha is equal to beta is equal to 0, but with delta wall interface, then these are the Coulomb's earth pressure coefficients which are given here, and here pi dash is indicated as a drained interface friction angle, drained friction angle. Then for the effect of wall friction on lateral earth pressure, you can see for this is a wall friction angle in case of delta A with a positive and negative wall friction angle, and here in this case with KPC, that is for when delta P is equal to 0, these are nothing but the Rankine's coefficients, that is Coulomb's earth pressure coefficients are equal to Rankine's coefficients, that is Ka. So, for example, here at for phi is equal to 30, delta A is equal to 0, as you can see that for phi is equal to 30, delta A is equal to 0, it is nothing but 1 minus sin 30 by 1 plus sin 30, and which gives 0.333. Similarly, for pi is equal to 30, for KPC change to KP, delta P is equal to 0, it is nothing but 3. So, as you can see that the variation of as the wall interface friction angle is varying, then there is variation in these earth pressure coefficients which are shown in this table form for reference. Now, let us see having looked into this Coulomb's earth pressure, there are also graphical methods for arriving at this earth pressure. Many graphical methods are there, but the famous one is Coulomb's method. The Coulomb's method involves what you need to do is that you have to represent the wall dimensions to a scale on a graph paper, on a millimeter graph paper. That means that a selected scale has to be made, and the wall has to be with proper inclination, and the wall has to be drawn onto the graph paper with the proper scale. Then one has to draw slopes line, that is inclination with horizontal phi, and along that line also you need to draw the slope surface or a backfill surface. So, backfill surface is inclined with horizontal, or sometimes beta is equal to 0. So, with that we will be able to so by drawing a number of trail failure lines passing through the heel of the wall, draw the number of failure lines. So, in case if you have got say uneven surfaces, or if there is a berm which is need to be considered in the analysis for calculating the active thrust, this is possible. This graphic method, which is very robustic in adopting and calculating earth pressures. So, let us look into this procedure, and we will try to look into the problems in how the external loads can be calculated, and how we can do in case of active, and how we can do this in case of passive case. So, this involves, as we look into this is for the case of a positive wall friction, that is the wall resting on a firm foundation. AB is the wall surface which is considered as vertical in this case. Now, this is that surface, that is ground surface is drawn, and this is the horizontal, and this is the heel of the wall. Now, draw weight line or a slope line at an inclination phi dash with the horizontal. So, first draw the weight line or a slope line with an inclination phi dash to the horizontal. This represents, as it represents the natural slope of the backfill. So, this is drawn like this. Now, draw trail wedges, like this is the first trail wedge. We do not know whether this can be this qualifies for the potential failure wedge or not. So, we need to draw a number of trail wedge surfaces. So, this is A1 is the first wedge surface, AB1 is the first wedge. Similarly, so once you have drawn AB1 as the wedge, determine the weight of this wedge, that is per meter width, per meter length, AB1 gamma is known to you, you calculate what is the weight, and that weight is plotted onto a scale, on a suitable scale on the weight line or a slope line. So, AB1 weight is indicated as say some point A dash. Okay. Now, at an inclination of psi is equal to alpha minus delta, which is this angle is nothing but angle between W and PA, active thrust and W. We have seen this in the previous slide. This can be seen in this slide, where in this Coulombs graphical method, this is that force triangle PA or resistance. So, psi is equal to alpha minus delta. The same problem we are trying to solve by using graphical method. So, similar thing we have done by using analytical method, and we try to obtain the Coulomb's earth pressure coefficients in active case and passive case. So, similar problem, but in case this particular method is very easy to consider even uneven surfaces or to consider the berm, or in case if you are having a railway track and there is a line load acting at one point and another point, and these effect of these line loads, and then the net active thrust can be calculated very easily. So, that we look into the procedure. Now, once again, draw this earth pressure line. This earth pressure line has to be drawn at psi, which is equal to alpha minus delta inclination from the slope line. Please note, the earth pressure line has to be inclined from has to have inclination of psi equal to, which is actually has to be from alpha minus delta. Now, having drawn trail wedges, number of trail wedges. Now, AB2 is the next trail wedge, AB3 is third trail wedge, AB4 is fourth trail wedge. Like that, you can have trail wedge. If at all you have a trail wedge or in a surface which actually changes elevation and all, we need to take the wedge passing through that particular point. So, after having obtained, what we need to do is that this line is nothing but weight of AB1 represented to a scale on this line, and these two distance between these 2 points is nothing but the weight of the wedge AB2, and distance between these 2 points nothing but the weight of wedge AB3. Similarly, this point is nothing but the weight of the wedge AB4. Now, from these points, draw a line parallel to the earth pressure line, that is this line. So, draw a line, see and where it cuts, that is the point where it cuts, then this point where it cuts, that is line A2, and this is the point where it cuts A3. Similarly, this is the point where it cuts A4. Now, what you will get is that joining these we get the Coulombs envelope. This is nothing but the earth pressure locus. So, now we can draw a line parallel to this slope line. Draw a line parallel to the slope line, and wherever it is tangential, and that is the point where it gives that maximum PA, that is the maximum PA, and the line passing through that, which was shown before itself, which generally we will not know, we will be knowing only in the end, and this is that possible failure wedge, potential failure wedge, which actually gives that maximum PA. So, here that PA, which is actually shown here, and this ordinate now you have to measure, and then to the weight scale it has to be given as that active earth pressure, active thrust PA. The similar problem, now if you have got say Q kilonewton per meter, say railway track load which is actually at this point, say AB is the wall surface. Now, if you assume that this is that surface which is having is uneven surface, the actual surface is not having any inclination. So, very difficult to consider in analytical method, but in the graphical method it is very easy to consider. So, suppose AC1 is horizontal, C1, C2 has got certain slope, C2, C3 has got certain slope. So, it has been considered like this, but only difference is that here there is a line load or a boundary wall is there which exerts a load. So, now in a similar procedure, draw the slope line with that phi and draw that pressure line. So, this is for extending external line load on the backfill surface. So, from through the heel of the wall, draw innumerable number of surfaces, but make sure that your wedge line passes to the point C1 and C2 is the location. For example, if there is a load at C3, suppose another load Q2 is there, and that also has to be considered. So, like this, or if there is another load which is acting at this point, and that has to be considered. So, similar procedure by plotting the weights of these wedges on this slope line and drawing a line parallel to this surface, we will be able to get this Coulombs envelope, and this hump which is actually caused, because up to here you need not consider the weight of this the extra load, additional load caused due to external load, but moment you reach this sledge, that is this wedge, you need to consider the weight of that particular load which is coming at that particular point. So, in this case, because of this, the envelope gets projected and then it goes. So, this envelope which gives is the envelope with line load, and this is the same envelope without any line load. So, again by drawing a line parallel to this and parallel to this, you will be able to get the PA, which is nothing but active at pressure thrust, which is can be obtained graphically here by measuring Emax is equal to EA is equal to PA. We will be able to get the converting into the scale, we will be able to get what is that PA with line load and without line load. So, like this we will be able to do this by representing this into this scale and then trying to solve these problems for either active case or passive case. This can be adopted for calculating that pressure. And here what we need to do is that we need to draw the geometry of the wall, like whatever that wall which is there, and this geometry has to be represented, and this surface, ground surface has to be drawn, and first the slope line has to be drawn with angle phi which is above the horizontal, and earth pressure line has to be drawn which is psi is equal to alpha minus delta. Then in this case an average angle alpha can be considered, and then we can plot these weights of these wedges on the slope line, and then draw lines parallel to that pressure line, which is not exactly parallel in this figure, but when you draw you will be able to see that it cuts this potential the trail wedge surface lines at point P1, P2, P3, P4 and P5, and at point where this load is there, and that point there that hump will be caused, that is because of the accounting for that load. So, subsequently when you are considering, you need to consider that load which is coming, but for a wedge, for example here we need not consider the effect of this particular load, only at this point when you consider, and then subsequently when you do, the envelope changes. So, by drawing a line parallel to this surface, we will get the Coulombs envelope here, and then we can calculate that active at pressure thrust, resultant thrust acting at a point h by 3 at certain location which is known location can be find out. So, in this lecture what we try to see is that we looked into the Coulombs theory and assumptions we discuss, and then we also discuss that the limitations which are with Coulombs theory, especially from the failure surface. The failure surface is assumed to be plane, but in reality it is because of the wall friction, it is having estimated as a log spiral theory, which actually deviates for the passive case. In case of active case, the deviation is minimal, and even in case of passive case, when for the delta, which is wall friction angle, is more than 1/3 of the internal friction of the soil, then we said that this theory gives unacceptable error which is very high. So, in the next class we will be discussing about application of the Rankine's method, or in a case where we can solve a typical problem with the Coulombs method, and we try to look into this, extend this to anchored bulkheads, and then try to see the stability of these walls in different conditions with and without water conditions.